Swayam Prabha. Digital India. Educated India.
Yeah, so welcome to this course on differential geometry. So I will in this first couple of lectures probably give you a broad outline about what we are going to talk about in this course, so that you have an idea of the content. Okay, so of course let me begin by asking some basic questions. Of course, the first question that you ask is, as they say, why should you do something at all? So the fundamental question is, why should you take this course? Why should you study differential geometry? Okay, and so let me write that down. Why study differential geometry? So to help us answer this kind of a question, which is of a philosophical nature, okay. So in order to answer this question, we can ask a few more questions. So the first question you can ask is, what is differential geometry all about? Okay, so let me write that down. What is differential geometry all about? So I will be using some abbreviations as I write, just to save time. Okay, so I've just written diff geom, which is supposed to mean differential geometry. Okay, then the other kind of question you can ask is, what kind of problems does differential geometry solve? What kind of problems it poses, and what kind of problems it solves? Okay, so what type of questions does differential geometry pose or answer? Okay, so this is the second question you can ask. And the third thing is, of course, connected with curiosity. Of course, all of inquiry, all of science, all of discovery has got to do with curiosity. You look at things around in life, in nature, and then you want to ask why such and such a thing is happening, especially when you don't expect it to happen. Then are there things in nature that you see which have a theoretical basis? And for example, are there things connected with differential geometry? So curious things, okay, you would like to see and understand, and there are many such things. Okay, so curiosity is one of the most important driving factors for anything in life. Okay, and without that, things will become very boring and dry. Okay, so that is what this third question is about. Examples of curious phenomena and results that can be proved using differential geometry. Okay, so these are three broad questions you can ask. Okay, and hopefully, by answering these questions, you get some drive to learn the subject and learn more. Okay, so let me start with the first one. What is differential geometry all about? So you see, if you want to say it in just one word, the answer is curvature. Okay, so it's all about what is called as curvature. And of course, I have put it in quotes because we put in quotes something that's not properly defined. You see, we want to approach it from a mathematical point of view. And in mathematics, of course, the important thing is proofs. Okay. You see, there are so many things that seem to be true, but then are they really true? That can be decided only if you give a proof. Mathematics, for example, is particularly a subject in which this is the most important thing to do. Okay. And how is it that you give a proof? The method is that you start with assuming certain things for true, things granted, they are called the axioms. Then from the axioms, you start making deductions. And then finally, you have a body of results. Smaller things that you prove are called as lemmas. And then you prove more, you put several lemmas together and you get a slightly bigger statement. At a bigger means at a higher level, less elementary, and you call that, these usually are called propositions, and then finally they culminate in what are called as theorems. Okay, so that's the pinnacle of this whole body of logic. So a proof is something, writing down a proof involves all this. You have to write down axioms, then from those axioms logically you have to build up and finally prove the statement that that you want to prove is actually true. Okay, so this is very much in mathematics. So when I say curvature has to be defined properly. Okay, and since I am not, that is going to happen in the following lectures, I am just going to put it in quotes. So whatever I am putting in quotes is like, or even if I don't put it in quotes, I am going to only say things which are heuristic, which you have an intuitive idea for. I'm not going to go into details. Okay, so this is only to give you a broad idea of what's going on. All right. So curvature, as the word suggests, is the degree to which something is curved. Okay, that's the simplest kind of statement that you can make. All right, and that's true. And of course, these are all all these qualifiers in English. The degree with respect to which something is curved. Okay, so this is all. It's very, very vague from a mathematical viewpoint. So we are going to really make that accurate, and we are going to do it for two basic types of geometric objects. These are going to be curves and surfaces. Okay, so this course is going to be only focusing on curves and surfaces, and curves can be curves on the plane, like the circle or parabola or any other curve, and you can also have curves in space. For example, the helix. Okay, and in the structure of the DNA, double helix occurs. Okay, and of course you see it also in screws and things like that. And then there are surfaces in 3 dimensions, like spheres and cones and cylinders and so on and so forth. Of course, there are the analogs of conics in surfaces. They're called conicoids. There are paraboloids, there are hyperboloids, and so on and so forth. Ellipsoids. Okay, so these are surfaces, and we want to understand how to study how much they are curved. Okay, so that's the whole that's the main focus in this course. Okay, and it's not that it ends here. This is only a first course. You can go the generality of mathematics is that you extend things from dimensions that you can perceive and see to dimensions that you cannot see. So for example, 4 dimensions and 5 dimensions and higher dimensions that you cannot really see, you cannot perceive, you can still handle it with mathematics, because the point is that the same axioms that you use to build the theory for 1 or 2 or 3 dimensions that you can really see and feel, those axioms can be generalized to n-dimensional space, and then you can have n-dimensional setup. And there you can start worrying about curvature of objects sitting in n dimensions. And so this goes on endlessly. Okay, so in this course, however, we will only worry about curves and surfaces. Okay, so and the idea is to understand how much they are curved. So now you see to get into one more level of understanding, a deeper level of understanding, you see, I would like to say something about, interaction of, geometry, which is mathematics, the mathematical point of view, and there's a lot of physics here. There's a lot of physical sciences here. Okay, so so there is a mathematical point of view, and then there is a physics point of view. Right? And at least if you, let me just illustrate this for the simplest objects that you want to study, namely curves. Okay, so the case in point is we are trying to understand what is the curvature of a curve. Okay, so what is the curvature of a curve? So from the physical point of view, it's a very simple question, and in fact it's a question that was posed by Newton. Namely, you take an object, ideally a point object, moving in space. Of course, it may move on a plane, doesn't matter, or it can move in space, and if you want, there is even a curved surface in space, for example a cone, or for example the surface of the earth, and there's something moving on it. Okay, and of course, because it's moving in space, it's not traveling in straight lines. Okay, so you all know the laws of physics, at least Newton's laws. When something is traveling in a straight line, you have laws for that. Okay, but then what are the other kinds of laws that you know? The other kinds of laws that you know are for circular motion also. So you have analogs of Newton's laws of motion for circular motion. Okay, and in general, if you take an object that's moving, what you can do is you can think of the movement as being in two pieces. One is a kind of linear motion and the other is a kind of curved motion. Okay, and for an extended object, there's also a rotational movement about the center of mass, and then the center of mass itself can be thought of as a point object, and its translatory motion can be taken, and put these things together, you get the total movement of the object. But we are only interested in a single point object and it's moving around. In general, it will move only in a curve. If it moves in a curve at any point, you will get an instantaneous velocity. Okay, and at that point, you see, since it's moving in a curve, at every point it is actually turning. Okay, of course, I don't want to consider the case when it is moving in a straight line, because you know the laws for that. I'm thinking of a honestly, curved motion. That means at every point it's turning around. So at every point there is some turning that's happening, and the path or the trajectory of the object is a curve, and you have to worry about how much it is curved at that point. How is that related? So as you can understand, at any point you can have the tangential velocity, the velocity of the object, and then at that instant, if you can fit a circle to the curve in a best possible way, then at that instant it is as if you are in circular motion. And the result of that is that you get a circle, and the center of the circle, so you get a circle, so you get a center of the circle, and then there's going to be a centripetal or centrifugal acceleration that will be along the radius of the circle. Okay, so basically the physics point of view is understand the circular motion of a point object. Let me put instantaneous. Okay, and write down the laws of motion for that. Okay, so basically the picture is like there's some path the object is traveling, and then you give me some point P. At that point there is a tangential velocity vector, and then at that point the idea is that you try to have a best fitting circle. Okay, because you are trying to approximate at that point by circular motion, and of course when I say approximate, so I am making a lot of vague statements. These have to be made mathematically precise. So I have a best fitting circle at this point, And this circle, it's not a very good picture I can draw of this, but let me try. And then the circle has a center and it has a radius. And of course, this is 90 degrees, all right? And then at that point, it looks as if this object is turning around that circle, and there is a centripetal, or centrifugal, whichever way you want to see it, acceleration. And then you would like to write down the equations of motion at that point, okay? So the point is that you want this circle, and you want to find this center, and you want to find this radius. Mind you, these are all time dependent. As you change the point, that's at a different point of time, you get a different circle. You can see that if the curve is very much curved, you see the circle becomes smaller. The more flatter the curve is, the circle becomes larger, okay? And you can guess in a limit that if it's really a part of a straight line, the best fitting circle will have infinite radius, okay? So this already gives you an idea how to approach the problem. See, this circle, if it exists, this circle is called the circle of curvature at the point P, okay? And this, the center of the circle is called the center of curvature. Okay, and this R is called the radius of curvature. Okay, and everything is at at the point P. So I should say circle of curvature at P, then center of curvature at the point P, then I should say radius of curvature at the point P. So it's dependent on the point. As you change the point, all these things change. Okay, now with this, it's very easy to define what curvature is. Curvature is nothing but the reciprocal of the radius of curvature. So curvature at P is 1 by radius of curvature at P. Why is this a good definition? If you ask for this question, okay, then you try to understand. If you are going to be in a portion of the curve which is curved a lot, your circle is going to be very small. The radius is going to be small, but the curvature is more. Okay, and more flatter the curve is, okay, the circle is going to be large, the radius is going to be large. So you can see that there is an inverse relationship between the curvature and the radius of curvature. And if you take the constant of proportionality as 1, you literally put curvature to be inverse of the radius of curvature. Okay, for a straight line, what happens? The best fitting circle is circle of infinite radius. Okay, and the curvature will be 1 by infinity, it will be 0. So straight lines have 0 curvature. If you take a circle at any point, for a circle, the best fitting circle is the circle itself, and the radius is the radius of the circle, and the radius of curvature will be 1 by that. And you see throughout the circle, the radius of curvature is constant, it is 1 by the radius. You see from this definition. Okay, so this is the completely physical point of view. All right, now so this is the usual kind of exchange between mathematics and physics, or for that matter mathematics and all sciences, that there's something you see in some science and then you immediately get some ideas. But then the problem with mathematics is proofs. Okay, now mathematicians, as mathematicians, the first question that one asks is, why should such a circle exist? So in mathematics, things just don't exist. You have to show that such a thing exists, and usually the way it is done is it exists, and there's one more thing. If it exists, is it unique? Are there more than one possibilities that satisfy the given condition? So in this case, I want a best fitting circle. This best fitting is not properly defined. Okay, but mathematically you have to refine it. So the mathematical part of it is to quantify all this. What do you mean by a best fitting circle? And if such a thing exists, show it exists, prove it exists. Then Well, if such a thing exists, I have the curvature, so that's a point. What are its coordinates? I have this circle of curvature, it has a radius. What is the formula for the radius of curvature? So math immediately asks you to put down all this. Unless you have done all that, it's not mathematically sound. Okay, so that is a math point of view. So, so if you see that this is how, in this case, math is inspired by, a real world question, right? And this is how it is for all applied sciences. Okay, there's something that you see in nature, something happens, and then you guess that geometrically something is happening, but then you need math to write out everything. Okay, so from the math point of view, it's very, very interesting. There are several views, but I will at least say, let me say something about two of these views. One is, of course, the geometric view, and the other is the calculus view. Okay, so the geometric view is more or less, the same. The idea is find a best fitting circle to the curve at a given point, and this best fitting is, the circle should be as close to the curve as you can expect among all possible circles passing through that point and having the same tangent. So you see, basically what I can do is, if you give me a point like this, I can draw several circles. Okay, with the same point, with the same tangent as this v vector at that point, I can draw lots of circles. I can draw a smaller circle like this, okay, or I can draw a much larger circle. Okay, all these circles pass through P. They have at P the tangent given by this tangent vector. I can draw many of them. In fact, I can draw things even on the other side. I can even draw a circle like this. Okay, so the question is, what do you mean by best fitting circle? You can say that, the portion of the arc of the circle is as close as possible to the portion of the arc of the curve. Okay, so, and as close as possible means you have to, for example, measure distances and try to say that if you somehow can estimate that, you would like that to be smallest. Okay, again, this is a refinement, but it's still not accurate. Okay, so this is a geometric point of view. Okay, but to make things accurate, you need to, you cannot anymore, dilly-dally with words. You will have to put in some concrete mathematics. Now, how do you put in some concrete mathematics? That's where calculus comes in. Okay, so the calculus point of view, it basically, gives you two things. The first thing is, in a nutshell, it gives an answer in a nutshell. What is differential geometry all about? I told you it's curvature. What is curvature? If you ask that question, the answer in a nutshell is second derivative. Okay, so it's all, that's the seed of everything. So it's the second derivative, and so this is something that is an extension of how the first derivative, for example, is used. If you go back and think about your basic calculus courses, what is the significance of first derivative? Physical significance of the first derivative is velocity, right? Instantaneous rate of change. All right, what is the mathematically, what is it? Mathematically, if you look at it, there's one and only one word that will come to your mind. It's tangents. So if you take, so for example, so let me write this down. First derivative is connected with tangents in mathematics, and if you go to physics, it's connected with velocity or instantaneous rate of change. Of course, when we say velocity, you write it as ds by dt, and where s is displacement, t is time. But in general, it also means dy by dx. dy by dx, where y is a function of x, that's also instantaneous change of y with respect to x. It's instantaneous with respect to x. Okay, so it's also velocity. All right. And of course, just to write this correctly or completely, the second derivative in the math part is going to be given by circle of curvature, etc. And I'm writing circle of curvature instead of curvature because I want a geometric object, not a property. Okay, so circle of curvature, and here in the physics part, it's of course, guess what it is? It's going to be acceleration. It's going to be acceleration. So you see, there's a complete analogy from the math side and from the physics side. Okay, so because it's a second derivative is second rate of change, and that's acceleration. Okay, first rate of change is velocity. All right, now you see, let me just recall. See, if you have a function, if you draw the graph of function y is equal to fx, okay, then at any point you draw the tangent, then the slope of the tangent is given by dy by dx, which is just f dash of x, right? That's how the first derivative gives you. So for a curve, dy by dx gives you basically it gives you the tangent line to the curve, and the tangent line is passing through that point anyway, so all you need to draw the line is just the slope, and that's exactly what the first derivative gives you. All right, and what about functions of more than one variable? It is the same old story. So if you take, for example, suppose I take a function. So this is, for example, a function from R to R. Okay, and this is the graph of a function from R to R. Okay, y is equal to fx. You could have taken a function from, let us say, R2 to R. Okay, and so let me use a different letter. Let me use capital F. So capital F from R to R, basically x comma y, point in R2 going to capital F of x comma y. You could take something like this. What happens in this case? Basically what happens is, what is the first derivative? The first derivative in this case, you see there are two variables, x and y are two independent variables. So you'll have two first derivatives, they are partial derivatives. Basically what you will get is that you will get fx and you will get fy. You will get two of them. Okay, and of course fy by fx is going to give you a slope basically. Okay, now you see, what is this? If you recall your first course in calculus, then you can draw what are called as level curves. So these are all loci on the plane where f is constant. So for example, on this on this curve, on this loop, you have f of x comma y is equal to c1, and on maybe here you will get f of x comma y is equal to c2. So these are what are called as level curves. Okay, why are they called level curves? Because the way the curve is plotted is at every point the function value is the same. So it's the same. So that's why it's called a And what is the speciality? How is the first derivative connected with these level curves? At any point, what is this? This is, by the way, this is grad f. This is the gradient. And what is the geometry? The geometric point is that the gradient is the normal to the level curve. So if you take this point here, this is given by gradient. This is the gradient direction. If you take a point here, then this normal direction is given by the gradient. So at every point, so these level curves are the loci where at every point the gradient is normal. Okay, and it's somewhat interesting that you don't get tangents, but you get normals. But understand that giving normals is the same as giving tangents, because once you give me the normal at a point, I can draw a line across it perpendicular to it, and that's my tangent. So there's really no difference between tangents and normals. You must understand that. Giving the normal and giving the tangent, they are the same. Okay, so you see here also how the first derivative is useful. And let me go one more step and take up function of three variables. Okay, then in this case you have x, y, z going to g of x, y, z, and now you are in 3 space. Okay, and what happens in this case? Just like in the 2-dimensional case, function of 2 variables, the gradient was the normal to the level curve. And what are the level curves? The loci where the function is constant. In the three-dimensional case also, you look at the loci where the function is constant. When a function of three variables is constant, you will get a surface. Okay. And this is going to be a level surface. And what's going to happen? The same old thing. If you take the gradient, it's going to be the normal to the level surface. That's all. Okay. And so what happens is that you get a surface like this, and this is a level surface. And you, at any point, you have the normal to that. That is given by the gradient. And this level surface is given by f equal to constant. Okay. So here again, only the normal comes. Where are the tangents? It's very simple, because you have surface. You give me the normal direction. Draw the tangent plane perpendicular to the normal. That's the tangent plane to the curve, to the surface. So basically, what you'll get is if you draw the norm plane through that point, which has this as normal, you get what is called the tangent plane. Of course, I am using TGT as abbreviation for tangent. Okay. And what is the beauty of this? This will contain all the tangents of all curves on the surface passing through that point. If you pass a curve through that point on the surface, its tangent, you draw its tangent, it will lie on this plane. Okay, that's what it contains. So you see very clearly the first derivative, whether it is first full derivative or whether it's first partial derivatives, they always give you tangents. That is the importance of first derivative. That is a mathematical significance. Physical significance is it gives you velocity. Okay, in the same way, the second derivative gives curvature. Mathematically, physically, it gives acceleration. Okay, so that is the point of view. Now let me come back to one simple calculus view is that curvature is the second derivative, but there is still something that needs to be substantiated. Namely, I told you in the geometric mathematical view, there is a best fitting circle. Okay, now what is this best fitting circle? Now that is again very vague. See, the point in mathematics is that nothing can be left vague. You have to finally define everything. Okay, and then you may be baffled that there are silly things which look so obvious, but which are even open as conjectures, they are not proved. So for example, my usual reference is to very simple statements in number theory, which is the most easiest one can think of in an elementary way, which are kind of open questions. For example, every even number is a sum of two primes. That's what is called the Goldbach conjecture. It's not proved as yet. Okay. Then the existence of twin primes, it's called the twin prime conjecture. Okay. So there are many statements. Twin primes are two primes separated by a difference of 2, like 11 and 13. So what you expect is that as you go down the list of primes, the primes are getting farther and farther away, and you expect that beyond a certain stage, maybe you cannot find two primes close enough with a distance of 2. And why 2? Even with some finite distance, because its primes are getting scattered, you don't expect. But recent progress has shown that there is a bound. People have been able to show. And bringing it down to 2 is a conjecture. But it's mind-boggling because you don't expect that to happen. So there are many things like this in math which are so simple but which are not proved. So mathematics is all about trying to prove, or at least try to build tools, theory to prove it. Okay. So to get back to whatever we are doing, you see, I'm just trying to stress that trying to make everything mathematically precise is also part of building the theory. I mean, that's the most important part of building the theory. So I made the statement that, what is a best fitting circle? What do you mean by best fitting circle? So with calculus, you can say that. So assume that, your curve has a nice, you can write the curve as a nice function, and to which you can apply calculus. And one of the nice things you can do with calculus is that you can write what is called a Taylor series. At least if the curve is differentiable n times, you can write a Taylor polynomial of order n, which will involve the first n derivatives. Okay. So the point is you take a nice curve, okay, of course it has to be nice because you have to apply calculus to it. If it is a curve which doesn't even have a tangent, I cannot even, that means I cannot even differentiate it, okay. So if I want to apply calculus to it, it should be a nice curve. And we are going to see that many things that we do in the course will heavily use calculus, okay, it uses multivariable calculus. So we will assume as many derivatives are available to us, okay. So you take this curve, assume at least up to second derivative, the curve has admits second derivatives, okay. And then what you do is up to second derivatives, and by the way, if you assume something exists without it being continuous, it's useless. So whenever you assume some derivatives of certain order exist, you assume that they are also continuous. So you assume that the curve has second derivatives and they are continuous. Then the point is you compare that with the standard equation of circle, which is also in two free variables, which is of the form x minus alpha the whole squared plus y minus beta the whole squared is equal to some r squared, okay. So it's an expansion in x and y, okay. And therefore what you do is that you can make this definition precise by saying the best fitting circle is the same as the circle for which you see up to the second order derivatives, the equation of the circle is already there in the Taylor polynomial of your function. So that is the most accurate way of doing it, okay. So this completely makes it a pakka without any vagueness. When you say that it's a best fitting circle, I am saying up to second order it must be the equation of the circle that you want. And you all know, you see, if I take a function f of x comma y, you write it as you expand it as a Taylor polynomial around a point x naught y naught. What will you get? You will get f function value at x naught y naught, okay. Then you will get first partial derivatives fx and fy, okay, multiplied by x minus x naught, y minus y naught, okay. That is the first order term, and that is the gradient part. That's going to give you the tangent plane or the tangent line, all right. Then you have the second derivative, because I told you curvature has got to do with the second derivative. What will be the second derivative? It will be f double x dou squared f by dou x squared, fxy dou squared f by dou x dou y, which you assume is dou squared f by dou y dou x because of Clairaut's theorem, assuming that up to the second partial derivatives are all continuous. And then you have f double y, which is dou squared f by dou y squared, and these are all going to be multiplied by the corresponding term. So fxx will be multiplied by x minus x naught whole squared, and you will get a factorial 2, and then you will get 2 fxy multiplied by x minus x naught into y minus y naught by factorial 2, all right. And then you will get similarly fyy at x naught y naught multiplied by y minus y naught the whole squared by factorial 2. That is the second order part of the Taylor expansion. Second order approximation, as you would have learned it in the multivariable calculus course. So the second order part is actually a quadratic part, and that's your circle. That should be your circle. So it's right there, right in front of you. That's the circle, okay. Now it's a matter of geometry and reasoning that you can check that this is the best fitting circle, okay. In whatever sense you want to check, you can check it geometrically or otherwise mathematically. So that's how it's made precise, okay. So I'll write it here as a circle. So this is supposed to be an abbreviation for circle, given by the second order term in the Taylor expansion or polynomial. Again, I am only still saying things very vaguely because I have to write down everything properly, okay. But I am just trying to give you a glimpse of what kind of things are involved, okay. So that is the calculus point of view. Now, you see, I can probably go ahead and say something about. So let me say some more curious things about curves before I move on to surfaces. And of course, this is more connected with these other two questions. What type of questions are posed in differential geometry? What kind of questions are answered? And what are the curious phenomena, results that you can come across and relate to? Okay, so let's focus on curves. Okay, so one of the important classical things that one comes across is what is called the isoperimetric problem. Okay, so results, curiosities connected with curves. So the first thing is the so-called isoperimetric inequality. So I'll tell you what this is all about. So you see, you take a loop, a closed curve, something in the form of a loop, okay, and then the idea is that so think of the loop as a rubber band, so that you can deform the shape, but you, of course, let it be I want it to be a rubber band only so that I can change the shape, not to stretch it or shrink it. That means I want the length to remain the same. So I have a closed curve of fixed length, okay, and then I want to look at the area inside, okay, and the question is that what shape will give you the maximum area, okay, and from a physical point of view, you will guess that it is a circle, okay, and any other thing should give you lesser area, right? Now you see, this is also something that you can physically see. Suppose I take a very thin piece of thread which is made into a loop, and put it on a plate, and in the inside of that I start pouring some liquid, let's say water. As the water goes and touches the thing, the loop, you expect it to become more or less circular. Or if you make a bubble out of it also, okay, you expect to get a spherical bubble, okay. Water droplets, when they fall, they form spherical droplets, okay. Of course, there is an effect of gravity. If you do it in space, you'll get perfectly spherical drops, okay. So it's because of surface tension, the surface area is minimized for a given volume, okay. So in the same way, you expect physically that if I give you a loop, the maximum area for that loop comes only when it is in a circular shape. Now this is a physical observation, okay, and of course when you want to give an explanation for this using physics, you can use for example things like surface tension and so on and so forth. But again, in math you have to really prove it, okay, and mind you, when you prove things in mathematics, physical laws are not available. A proof in mathematics is, it's a plain statement without any reference to physics, okay, and amazingly you can make a statement in mathematics and you can prove it mathematically. So you see, this is another beauty, that there is something in physics that as a law, you can make experiments and you can verify it, and there are physical laws by which you can explain it. But then there is also happening mathematically. Even in mathematics, it's true. Without having any idea of physics, in mathematics you can see that the same truth is reflected, okay. And one of the examples is the isoperimetric inequality. Of all closed curves, the form of a loop of a given fixed perimeter, that's the reason for the word isoperimetric. Isoperimetric means having the same perimeter. The one shape of the loop that will give you maximum area is that of a circle, okay. So that's the inequality, and it's called an inequality because in other cases this is the maximum, the other cases you will get lesser area, okay. Now differential geometry allows you to prove this statement, okay. So that's one of the applications. Then we, of course, we will later on do this in detail, okay, but I just want to give you some of these results. The next thing is what is called the famous 4 vertex theorem, okay. So 4 vertex theorem, what is this 4 vertex theorem? Let me tell you in a in a very simple way, okay, very intuitive way. Suppose I start from a point, I start traveling, say, in one direction. To return to that point, you expect that you have to turn at least 4 times, right? So I turn once, then I turn once more, then 3 times, and then I come back. Okay, so you see that I have to make at least 4 turns to get back to the. Now this looks obvious. Of course, I can do this by always turning, by going on a circle. That in that case, I am continuously turning. Okay, but can you do it by turning at minimum number of places? What is the minimum number of places at which you can turn so that you can do it? That's 4. Okay. Now, this looks so obvious and it looks very natural. The point is, it has to be mathematically proved, and it can be mathematically proved using differential geometry. So this is the famous 4 vertex theorem, and it was discovered by an Indian mathematician. Okay. So this is another interesting result that you can prove. Okay. So maybe I will stop at this point. We will continue tomorrow. I will tell you more about some other interesting things. So I will stop here.